Thank you, Yi Kwang, and thank you all for having me today. This is my first time visiting ASIAA and Taipei, hopefully the first of many. And so until Friday, I will be in room 1108. So please come talk to me if you're interested in field level inference or just cosmology from galaxy surveys in general. To set the stage for this talk, I want to clarify from my title that decoding the cosmos means that inferring or measuring the growth of large-scale structure. And the cosmic large-scale structure is basically the cosmic web of dark matter that we don't observe directly, and the galaxies that trace this underlying dark matter distribution. During the entire cosmic time, from tiny fluctuations in the early universe that can be described by this delta M quantity that I'm showing over here. Actually, I got a pool cue to show you. So this is basically the overdense or underdense, the local overdense or underdense of the matter density compared to the mean matter density of the universe. This is what I mean by matter density fluctuations. So over the entire cosmic time, from tiny fluctuations in the early universe, these grow into the large-scale structure that we observe today. And this is a consequence of a direct competition between gravitational collapse and gravitational interaction between dark matter and the background expansion of the universe driven by dark energy. So by studying the growth of large-scale structure, the temporal evolution of these fluctuations, we directly have a window to directly look into nature of gravity, dark matter, dark energy, and their interplays. A key quantity that will keep coming back in this talk and a key proxy for the growth of large-scale structure is this quantity sigma 8 I'm showing over here. Roughly speaking, this is the variance or standard deviation of matter fluctuations within spheres of roughly 8 megaparsec over h. So to compare the observations to the theory, what cosmologists usually do is to make a summary statistic of the data, and the workhorse of cosmology up until now is the two-point correlation function, or its Fourier transform, the power spectrum of density fluctuations. The power spectrum of density fluctuations characterize the fluctuations, the power in the fluctuations as a function of scale. So in Fourier space, basically the Fourier wave number goes at inverse of the separation scale. So here, high Fourier wave number over here means small scales, and low Fourier wave number over there means large scales. What is the information content in this power spectrum? Well, the slope of the power spectrum tells you about the cosmological parameter NS, the spectral index, characterize the scale dependence of bimodal fluctuations in the early universe, and then the scale of the power spectrum turnover, so the peak of the power spectrum here, and the baryonic acoustic oscillation wiggles over here are determined by the matter and baryon density parameters. Finally, even though sigma 8 is an integral of the power spectrum over a range of Fourier wave number k, it can also be related to the amplitude of this matter power spectrum. What I'm showing you is the matter power spectrum at redshift 0. Notice the z equal to 0 over there. But in cosmology, as we look further in space, we're looking back in time. So we always look back in time. We never measure the power spectrum today. Rather, we measure the power spectrum at some distant redshift, so in the past. And these power spectrum can be related back to the power spectrum today. Very simple. In linear theory, it is just by the linear growth factor and linear growth rate. They are quantities depending on the cosmological parameters that I showed you earlier. And this linear evolution only change the amplitude, vary the amplitude of this matter power spectrum. So the name of the game for cosmology is really to measure the power spectrum of large-scale structure at different redshifts, different points in time, and then by comparing them, we can try to see whether the underlying theory of the universe, the current standard model, provide a consistent prediction for different times. So the earliest snapshot of the power spectrum that we have come from the observations of cosmic microwave backgrounds, the CMB, and then the other large-scale structure probes, including galaxy clustering, which is the focus of this talk, and galaxy wick cleansing, plus many others, probe typically the late-time universe, lower redshift, from 0 up to like 2 to 3. And in recent years, the comparison and observations between CMB and large-scale structure probes have led to something we know now as the SA tension. And this is a busy plot, so bear with me as I walk you through it. Maybe just focus on the x-axis for now. The x-axis is showing the S8 parameter. This is a combination of the matter fluctuation amplitude sigma 8 and the matter density omega m. This particular combination is well constrained by galaxy weak lensing, so that's why we usually use it when we compare the constraints. So if you take the constraints from cosmic microwave background large-scale power spectrum and the large-scale structure power spectrum in terms of sigma 8, you will see that these horizontal bars, red for CMB and blue for large-scale structure, they are roughly in 3 sigma tension with each other. This is what is known as the S8 tension. Now, what does this mean? What is the possible interpretation if this is of physical origin? For that, we can now switch the focus to the y-axis. The y-axis is the growth index. This is a parameterization of the linear growth rate that I introduced earlier. So omega f equal to omega m raised to the power of gamma. And within general relativity and lambda CDM, there's a very specific prediction for gamma, which is 0.55. This is up to the precision of 0.1%. So if you detect any deviation of gamma from this particular value, you probably or possibly are seeing some departure of physics from the standard model, including the departure of gravity from general relativity. And so in this particular paper, we allow gamma to be free. We introduce this additional freedom into the model. And when we look at the CMB and large-scale structure probes individually, we can see that they both prefer a higher growth index compared to the value of 0.55 that gamma lambda CDM predicts that I'm showing over here. So when this gamma is free, the constraints in terms of sigma S8, that you are seeing from CMB in red and large-scale structure in blue contours are also moving towards each other so that they are now statistically consistent. So one can say either that we rediscover the S8 tension, or one can say that we discovered something that is called growth suppression of large-scale structure, because recalling that here omega m is usually smaller than 1. So gamma a higher gamma means a smaller f, so a slower growth rate of large-scale structure. So that means that large-scale structure recently has been growing slower than the prediction by Einstein and general relativity as well as the standard model lambda CDM.
Sorry.
So, yes, please.
Why CMB gives degeneracy between that direction?
You mean the degeneracy? Sorry, you mean the degeneracy direction?
Yes. Yes.
Yeah, I think they both have some degeneracy between gamma and S8 because how gamma is introduced here, but it's just depending on the redshift of the power spectrum that you are seeing the different angles of the degeneracy. So large-scale structure tends to have this go this way, and then CMB will go that way.
But this way, the stronger gravity. This way, the weaker growth. Why?
So
it makes sense. This way it makes sense.
So smaller growth, slower growth rate is this way. Yeah.
Right.
Y-axis.
Yeah. And going up, prefer the S8 is lower. That also prefer the
slower S8. Yeah. Right. So slower S8 and higher gamma.
Yeah, so this just allows strong and weak growth. So why? Right.
So this is a good question because so S8 is basically always an extrapolation from the redshift that you measure the power spectrum to the current time, right? So depending on where you measure, so CMB you measure basically you measure the amplitude of power spectrum at a very early time and you extrapolate. So if the growth rate of large-scale structure is smaller, as you extrapolate more and more, you will get a smaller S8, right? So slower growth rate, but the same amplitude that you measure at some redshift mean a lower S8 at the current time. Yes. Okay, good.
Sorry, following up to his
please.
question. So where, like the information about gamma come from CMB? Like it's 2D, like the
Is it
power spectrum.
right? Good. Yeah. So here, by CMB, I didn't really explain what I mean by CMB. So CMB is, of course, the primary CMB, but the primary CMB is not what we actually observe. So the direct observable is the lens CMB, right? So gamma answer in the lensing of the CMB that we observe. Right.
Thank you.
Very good. Thank you. Sorry for mentioning that. Okay. Yeah. So let's assume that the SA tension is of physical origin. A departure from gravity, from general relativity is only one possible answer. There are many possible explanations, including also physics on small scale that can come from either dark matter or just baryonic physics, or the processes that can be relevant for galaxy formation or evolution, but very complicated. So how do we know? Where do we look to be sure? In this particular plot, I'm showing all the probes of large-scale structure, and in this plan, going from top to bottom is going from early universe to late universe. Left to right is going from large scale, where the perturbations are linear, very small compared to 1, to the small scales where perturbations become strongly nonlinear. So you can see that galaxy weak lensing typically probes the late universe, but also up to very small scales. And then the primary CMB probes early universe on only large scales. So if there is tension between these two, it's very hard to distinguish, to tell whether the physics that's driving the tension is coming from difference between early and late universe or small and large scales. Fortunately, in this particular plan, there is this unique probe that is called galaxy clustering. I will explain why this is ISD/clustering later. But this particular probe is probing the late universe, but the analysis can be restricted to up onto quasi-linear scales. This is very good because on these scales we understand the theory well. We can isolate and effectively marginalize over on the complicated physics on small scale. So if we detect the SA tension using only galaxy clustering, that will give us a clear indication or interpretation of what is the physics driving this tension. So we want the best constraint we can have from S8 from galaxy clustering alone. But I will show, as I will show in this talk, in order to get us there, we probably need new tools and methods to analyze the data, to maximize the information that we have from the data. So I think hopefully that sets the stage. So this is the outline for the rest of the talk. I will be talking about the current state of galaxy surveys, going from the galaxy maps to statistics and to cosmology, using the example of the crescent DESI DR1 galaxy clustering analysis using the power spectrum. And then I will introduce this new field-level statistic and inference from galaxy maps that hopefully can do better than the power spectrum, or even the combination of the power spectrum and the next endpoint statistic, which is the bispectrum, and then discuss progress we are trying to make to apply this field-level inference to the real data. If time allows, finally, I will talk about how we can use this for astrophysics using cross-correlation measurements. So let's have a quick look about the dark energy spectroscopic instrument. This is an instrument mounted on the Mayon telescope, located just below the summit of the Kitt Peak in the desert, sorry. I've been thinking about deserts all day. Desert of Tucson, Arizona. And so for 5 years of operation, the plan is to map out the three-dimensional maps of galaxies from all the way from redshift 0 to 3.5 using 4 different types of tracers, from bright central galaxies to luminous red galaxies, emission light galaxies, and then finally the quasars or Lyman alpha forest that trace the high redshift neutral hydrogen. Predecessors of DESI is the Sloan Digital Sky Survey, SDSS, and as you can see, going from SDSS to DESI, the observing strategy and operation has made a huge progress. Namely, we have gone from using plug plates that require a human to change the plates and then plug and unplug the cables to robotic fiber positioners that can observe up to 5,000 objects in roughly every 20 minutes. And this explains why DESI has been so successful, always been ahead of schedule despite COVID, wildfire, and cyber attack. Unfortunately, on the analysis side, on the data analysis, there has been not much of a change, and we're still using mostly the infrastructure from the SDSS day. But of course, spoiler alert, we can do better with field-level inference. That would be the second part of my talk. But let me stay with the DESI story for now. So this is the DR1. This is the data from the first year of observation from DESI, showing in green on the left. And then for reference, I'm showing the full data sample, the full footprint in blue, and then the final data release from SDSS in red. On the right are the co-moving number densities. So how dense the tracers that are introduced earlier should look like from the for DR1 in the 6 redshift bins that we determine for this kind of analysis. So we put these galaxies, the 4 types of tracers, into 6 redshift bins before we analyze the data. We want to compare the DESI data to theory, but there are a few complications that we have to account for before we can do that. And the first complication is the fact that we're observing galaxies in redshift space. This means that instead of measuring the radial distance to these galaxies directly, we are measuring the Doppler redshift in order to infer the distance. So the Doppler redshift has one contribution from the peculiar motion of the galaxy along the line of sight. And this peculiar motion is because of the gravitational evolution of the large scale structure. So on very large scales, the galaxies just fall into the gravitational potential well, right? So this introduces like a squashing effect that is usually referred to as the Kaiser effect over here. And then on small scale, because galaxies move kind of randomly within the halo, this introduces like a stretching effect that usually people refer to as the finger of God effect. So in this animation on the right, you can see as I change the strength of gravity, so as I increase gravity, you can see the finger of God kind of pops out already for the dense regions over here. And hopefully you can also see the Kaiser effect on very large scales, but less prominent. So this turns out to be a blessing in disguise because this complication is linked to gravity, to gravitational evolution. So when you model it, you actually have access to the to gravity, to the growth rate of large scale structure, the linear growth rate f that I'm showing over there. And what we typically do in cosmology is we expand the galaxy power spectrum in multiple, and then we measure the first few non-zero multiples. In this case, in the case of DESI, the monopole and the quadrupole, the power spectrum. So the power spectrum of galaxy average over the entire sky, the monopole, and average over 1/4 of the sky, the quadrupole. By comparing the amplitudes of these monopole and quadrupole, you can get out the parameter combination f sigma 8. So you get a constraint on f sigma 8 through the redshift space distortion information. Okay. So the second complication is not a blessing, it's really just a complication. It's the fact that we do not observe dark matter directly. We observe galaxies, and galaxies are biased tracers of the underlying distribution of large scale matter. So in this cartoon, you can think about it as how galaxy formation respond to long wavelength perturbations. And let me consider a simple toy model where galaxies only form where the spatial density, matter density fluctuations is above a certain fixed threshold. So if you think of matter density fluctuations as a combination of in Fourier space of long wavelength perturbations, so perturbation on large scale, and small wavelength perturbations, so perturbations on small scale, you can see that the long wavelength perturbations will modulate the overall density fluctuations such that you tend to form more galaxies over here compared to here. And because of this response of galaxy formation to long wavelength perturbations, this introduces an additional modulation in the galaxy power spectrum or galaxy density fields such that the sigma 8 parameter that we are interested in is perfectly degenerates with the galaxy bias coefficient B delta in linear theory. Put another way, when you measure only the galaxy power spectrum monopole, you cannot tell whether you are measuring high sigma 8 and low B delta or high B delta and low sigma 8. So this is a perfect degeneracy in linear theory. So there's no way to get sigma 8 just by the galaxy power spectrum monopole. That's what I'm trying to say here. So galaxies are biased tracers of the underlying large scale structure, so we need a way to account for that. And currently in cosmology, the popular approach is this effective field theory framework that actually your neighbor Daniel Baumann put forward a few years ago. And the idea essentially relies on this simple fact that we live in a universe dominated by cold dark matter. So the galaxy formation can span the whole cosmic time. So this is the time axis, the y-axis in this cartoon. But during this entire time, the spatial regions where the matter that makes up the galaxy come from are actually very restricted. So that's why the elongated spaghetti that I'm showing here. So if we restrict our description of the galaxy density fields to very large scales, we can stay away from this region and we can effectively parameterize and marginalize over all the small scale physics that happen within this very small region of the spaghetti over there. This will allow you to write out an effective expansion of the galaxy density field on large scales, where the expansion relies on operators constructed out of the matter density field also on large scales. And at each order of this expansion, the operators are really determined by the underlying symmetry of the theory. This is the principle of the EFT approach. For this case, the underlying theory is gravity. So the symmetry is really the equivalence principle, and that will tell you exactly at each order what are the operators should be. The small scale physics that we marginalize over, they cannot just magically disappear. They have to be parameterized and contribute into this expansion in terms of stochastic contribution, and then you will fit these free coefficients in the data when you fit the data. So this is exactly what DESI did for the DR1. We measure the galaxy monopole and quadrupoles in 6 redshift bins for 4 different types of tracers. Using the EFT approach, we were able to write down the galaxy power spectrum that will be fit to the data. So this is the prediction, and then these are the EFT counter terms and stochastic contributions that I told you earlier that we will now have to fit these free coefficients to the data. And turns out this produced a very excellent fit to the data, as you can see here in all redshift bins. So the points are the data, and then the fits are the EFT fit, the best fit. So with that results, we can now, DESI DR1 can weigh into the SA tension, or the question whether gravity still behaves like Einstein general relativity. So in this on the left, the circles are the measurements from DESI DR1, and then the squares are from SSS from the DESI's precessors. The y-axis is this linear growth rate combination F sigma 8. Remember, because we only have access to F sigma 8, we don't have access to separate F and sigma 8. And these the standard model general relativity lambda CM are shown by the dashed line. That's the prediction from the standard model. And then different color lines are different models with different strengths of modified gravity. So from this plot, one could say that DESI measurements are consistent with lambda CDM, with the general relativity. And then on the right are the SA tension or SA constraints, again showing the DESI measurements in here compared to, for example, SIMB measurements in orange, and then galaxy weak lensing constraints in green. So you can see again the manifestation of the SA tension between CMB and galaxy weak lensing. But for DESI, I would say within lambda CDM, DESI constraints on S8 are consistent with both, although the error bars here are not very satisfying. And that leads me to the next part of the talk, which is that even with the most powerful data that we're having, what we are getting out is not very satisfying and nowhere near the statistical precision that we need to be able to say something about the SA tension or to be able to detect any new physics. So we need to get more out of the data. All right. So the second part of the talk will be about, again, getting more out of data using a new framework that we call field level inference. And so the idea here is that, again, remember I said that we cannot get sigma 8 directly from the data using only the power spectrum. We need the redshift phase distortion, but even then we only get F sigma 8. So is there a way to get just sigma 8 even without redshift phase distortion? The answer is yes. You need to go beyond linear theory, and you need to go beyond the power spectrum. So the most natural next step is going from beyond the power spectrum is to go to the 3-point correlation functions or the bispectrum. So measuring triangles on the sky instead of sticks. But what we are now proposing is just forget or skip on data compression steps and instead analyze the data directly as how we collect them. So imagine you giving me a galaxy catalog or galaxy maps in 3D, and now I just put that in a 3D box and then discretize them on the 3D grid. Because on computers, we want to deal with discretized quantities, right? So that will give you a presentation of the 3D galaxy field or 3D galaxy density field where each voxel, each grid point, or each Fourier modes are a free parameter that your model will now try to predict and fit to the data, instead of fitting the power spectrum bins, for example.
Sorry,
Yeah.
to clarify, even though you consider the field itself,
Yes.
that position is includes rest-free distortion. I'm confused with the constraint sigma without rest-free distortion.
Oh, yes.
Contain rest-free distortion.
Right. So yes. Thanks for the question. So, of course, in the end, when you connect to the data, you still need to account for residual distortion. But here, what the point I'm trying to make here is that when you analyze the data at the field level, even if you analyze for example, n-body halos from simulations in co-moving rest frame where there's no effect of residual distortion, you can still get the constraint on sigma 8. This would not be the case for the power spectrum, right? So the question is whether we still need to account for residual distortion in this approach. Yes, the answer is yes. But the point here is that forget about residual distortion. If you can even measure the position of the galaxy directly, and then you analyze using the power spectrum, there will be no way to get sigma 8 because how galaxy bias. But using field of inference, you can break this degeneracy because you have access to the nonlinear information. Yeah, sorry, that's might be a confusing title. Okay, so so here this is the spoiler for the main part of the talk. When we analyze the same data from simulations, so these are n-body simulations of large-scale structure where you can identify n-body halos. These halos are typically thought of as the host of the galaxies that we now observe on the sky. So these n-body halos are bias tracers of the underlying large-scale structure, just as the galaxies are. So when we analyze this data using the combination of power spectrum plus bispectrum, compare that to the field level inference where we analyze the entire galaxy density field. These are the constraints in yellow and blue respectively. So you can see that in both cases, you can get a constraint on sigma 8, breaking the degeneracy between bias, B delta and sigma 8, right? But using field level inference, the improvement factor of how tight the constraint on sigma 8 are tightened by a factor of 3 to 5. So to put this in context, improving the constraint on sigma 8 by a factor of 3 to 5 means that you're effectively increasing the volume of your galaxy surveys by an order of magnitude to 25 times. And this wouldn't be happen in one or even two generations of galaxy surveys. So instead of waiting for the successors of DESI, now you can use the DESI data but getting an improvement by a factor of 5 if you can analyze the DESI data using field level inference. So this sounds too good to be true, so maybe let me describe how we actually do it. So doing field level inference means that we start from the Gaussian initial conditions. So we start from the density fluctuations in the early universe where they look very Gaussian. And then for each single realization of this field, we forward evolve the realization to the redshift observation where we can construct a model prediction for the galaxy density fields that we will observe. This can be done in the EFT language, just like I explained to you earlier. Now we compare the model prediction to the data for individual Fourier modes or for individual grid points of this volume, of the survey volume. This sounds very challenging because if individual grid point is a parameter, then to cover the whole survey volume, you probably need 1 million of parameters, right? But turns out this now can be done very efficiently for so long as you have access to the gradients of the problem, so long as you know how, for example, a variation of the data over here, how a variation of the data over here affects the initial conditions. So that means that the forward model has to be differentiable so that you have a way to access this gradient information. So the requirements are the forward model to be very robust and accurate even at the field level, and it has to be differentiable. Even then, even with these gradient-based sampling methods, it has still to be fast because you have to do this process hundreds of thousands of times. If you ever done any Monte Carlo Markov chain fitting, you know that you need to repeat the process in order to get enough samples. So all of these requirements are calling for this, again, this EFT approach, and then that's why we have been developing this framework called LEFT fields, Lagrangian effective field theory for cosmology density fields. So again, the left field model, the left field framework relies on the EFT forward model that I already explained earlier to connect the matter density field and the galaxy field, and then a field level likelihood to compare individual Fourier modes between model prediction and the data. But that's it. That's how the framework works. Let me show you how this works also in practice. So here in this animation, the top is showing the log likelihood function. So how likely the data is given the model prediction. And then because the data is a cube and I cannot visualize a cube, so I'm showing here 4 2D slices over the 3D cube of the data on the top row. And in the bottom row, I'm showing the model prediction, the same slices through the cube of model prediction. We start with something very homogeneous for the prediction because we don't know what the data should look like. But as soon as you start the sampler, our sampler can, because it has access to the gradients, so it's very quickly can identify a configuration that can match the data nicely. And you can see that the log likelihood function keeps changing, showing that the model or the sampler finds the prediction that fits the data better and better. And this is actually like a slow animation where I have to slow things down so that you can see how it's changing. In practice, we can identify the configuration that match data in matters of a few seconds to minutes. Okay, so coming back to the results again, in this paper, we show that when we analyze this exact same data down to the same Fourier modes, using power spectrum plus bispectrum combination and field level inference, we're seeing a huge improvement using field level inference, using the entire data without any data compressions. So left and right are 2 different cases, 2 different simulations, 2 different redshifts, but the improvements are quite robust, and the general conclusion is that field level inference will give you significant improvements in terms of constraining the parameter sigma 8 in this case. So this is also recognized recently by the Bukata Cosmology Committee as showing promising potential to connect for the application to observe data. And so the next step for us, many of us are working on now, is to connect field level inference to the real observational data. And as Tepe asked earlier, one step would be to account for redshift phase distortion. And remember that the constraints I'm showing here, the improvements that I'm showing, are without redshift phase distortion. So when we finally account for redshift phase distortion and connect that to the data, we will have additional information gain. So this is independent of what I already showed you. This is led by Julia Stadler. She's a postdoc at MPA. And for redshift phase distortion, what you want to do is to displace the galaxy density field that the model predicts from real space to redshift space. And so you need access to the displacement fields of galaxies. And this is just to show you the displacement fields projected along the line of sight. So what really matters for redshift phase distortion, comparison between n-body simulation and the left field frameworks that we are developing. And you can see it's a perfect match between simulation and the forward model, although our forward model is 1,000 times faster than the full n-body simulations. The upshot is that model prediction that you want to produce in redshift space only costs about 1.5 times more expensive compared to the real space model that I have been using. So this is very promising, and we hopefully can fit the data efficiently still, even with redshift space distortion. Well, unfortunately, there are even more complications when you come to the real data, and one of them is what is known now as fiber collisions. This is the fact that, well, even as tiny as the fibers are, they still have a patterning radius, and also if the galaxy targets are too close on the sky, they cannot observe those target galaxies simultaneously. So this leads to like a missing of galaxies that are pairs of galaxies that are too close together, and so you have a suppression of the galaxy clustering on a small scale that you have to account for in your analysis. With field level inference, however, there's an advantage. You would be guessing that this effect would be density dependent, namely you would tend to have this happens more in regions on the sky where you have the higher density or higher projected density of galaxies, and you would be right. So in field level inference, you have access to this 3-dimensional density fields as a model prediction. So when you want to model that, you just need to project this 3D density field onto the sky, and then now fit a function of that to the data with some free coefficients. And that's the plan that I'm working on now at IPMU. Okay, so let me take a step back. and then talk about something not field level inference, but in general in the direction of going beyond the power spectrum, beyond the two-point correlation functions, the current workhorse of cosmology. So there's a growing community of people who are trying to do this, and we use many different methods, and people have been very creative. But one question that we keep getting is, how can we trust your analysis at the same level of confidence that we're trusting the 2 points of power spectrum analysis? And so as the first step towards the answer to this question, our community are coming together and starting this blind data challenge where we analyze the data without knowing the true underlying cosmology and trying to recover the true underlying cosmology, trying to convince ourselves that our methods are actually robust and we can trust our analysis, and other people can also trust our analysis as well. So within this data challenge, there are multiple challenges, but because field level inference only can apply to real space so far, so there's no redshift space distortion yet. So we're still working on that. So I will only show the results of the data challenge for the real space snapshot. In this particular context, there are 2 teams, and the other team also happens to use the combination of power spectrum plus bispectrum that I explained to you earlier. So when you compare the constraints between field level inference and power spectrum plus bispectrum for the same data, in this case using different analysis choices, you can see that both constraints are unbiased, and the constraints from field level inference are very competitive, but not as significantly as an improvement over power spectrum plus bispectrum. Why? Because in this case, you can notice that the maximum scale of our analysis only go up to 0.1, while the maximum scale of this analysis go to a much more aggressive scale. So this is all to say that even at a more conservative analysis scale, field level inference is still showing promising potential and getting you more information out of the data. So to me, this is still a promising conclusion. So finally, on my end, I'm trying to push this forward. And so as I said, there are many survey systematics that we do not know yet how they affect beyond 2-point statistics, not only field level inference. So we are trying in this September to organize a workshop at IPMU together with Linda and Leander over there to bring together experts from 2 communities, one working on beyond 2-point statistics of large scale structure and one working on survey systematics, to hopefully initialize discussion and then map out the community program of how to solve this problem of survey systematics for beyond 2-point statistics. Okay, so turns out I think I still have a little bit of time, so maybe let me keep my promise and talk about astrophysical applications of field level inference. This is something I'm very excited about, but it has been kind of pushed to the side because we have been busy working on connecting field level inference to data for cosmology. But if somebody here have any ideas or interesting idea, please come talk to me. The idea is that I showed you that we have access to not only, or we are fitting not only the cosmological parameters, but we're also fitting the entire galaxy fields or the entire underlying large-scale structure fields, right? So we have access to these fields. So we should do something with it. It's not just the parameters that you eventually forget about or marginalize over. And so one thing you can do, and I tried in the past where I fixed all the cosmology, and I just tried to use this framework as a reconstruction machine to reconstruct the underlying large-scale structure. Then what I can do is, given a reconstruction, I can create templates for different observations in different wavelengths and try to cross-correlate these templates with the external data sets. One problem that I looked at is the problem of missing baryons. So the problem is basically the fact that when we look at the baryons inside a galaxy cluster, for example, we count them, the fraction seems to be below of the cosmic fraction predicted by Big Bang nucleon synthesis. However, this can be explained by the fact that maybe the baryons are there, but they are not hot enough so that you don't see them when you look at them in the X-ray or the thermal Sunyaev-Zeldovich effect. One way to look for those missing baryons is the kinematic Sunyaev-Zeldovich effect, where you can use the fact that CMB photons on the way to us are Thomson scatter, so that if the galaxies are moving away or towards us, they produce an enhancement or decreasing of the CMB black body temperature. So this requires us to know not only the location of galaxy cluster, but also the radial motion of the galaxy cluster, whether it should move towards us or away from us. So in this reconstruction, I have the underlying large-scale structure fields. It's a forward model, so I also have the displacement fields. So I can now create, assuming an astrophysics model for how baryons and electrons are distributed within galaxy cluster, I can create it like a template for the kinematic SE signal that we should observe in the CMB map. And now I cross-correlate that with the CMB map. That gives me the measurement of the amplitude of this signal. So in the plot on the right here, I'm showing you the amplitude of the KC signal, which again can be thought as a proxy for the fraction of baryons inside of the cluster as a function of the relative cluster size. So 1 corresponds to the typical cluster size in the sample, and 1 here on the y-axis means the cosmic fraction of baryons. So this particular measurement kind of shows you that, well, the error bars are still big, of course, but it kind of tells you that when you look in the KSE effect, the fractions of baryons are kind of consistent with the cosmic fraction that you expect. Okay, finally is another astrophysics application. It's called galaxy intrinsic alignment. It's the fact that, well, galaxies are not isolated islands. If they were isolated islands, they would be like gravitational collapse, so they would be like spherical balls. But because they are embedded in the large-scale structure, so the large-scale structure tidal field can squeeze or stretch these galaxies so that they obtain some shapes aligning with the large-scale structure tidal fields. Again, I have access to the large-scale structure tidal field by this kind of field level inference or reconstruction. So I can use the large-scale tidal fields from the inference to create an estimate or prediction for the galaxy shapes if they were to align with the large-scale structure tidal fields. And this is exactly what we did in this paper. So for each individual galaxies in the sample where we have the measurement of their shapes, we also produce a prediction for the shapes that we should measure. So when we compare that between the prediction and the observations, we find that indeed galaxies tend to align with the large-scale structure within this linear alignment model that we consider, and the alignment can be traced up to very large scales. That tells you that the alignment of galaxy shapes, at least the red elliptical galaxies, to the large-scale structure tidal fields extends up to like 100 megaparsec over H. Okay, so I think I'm ending my talk hopefully a bit early, so we have time for questions. I introduced the current state of cosmology where we analyze the data using power spectrum and two-point statistics using DESI DR1 as an example. And then I talked about how to use field level inference to go hopefully beyond that to get more information from the data. And then the remaining steps that we are working on now to apply FLI on the data, including observational effects and survey systematics. And finally, some application of FLI to astrophysics that I'm very excited about, and hopefully some of you can tell me your idea of how to use it for astrophysics. Thank you.
Okay, thanks. Questions for him?
Yeah.
So you showed that, you know, the field level inference versus the cosmic aspects of like at scale, like inverse megaparsec. So what kind of additional information like field level inference capture, which is not captured by cosmic and light spectrum?
Right. So, for example, the easiest way to think about this would be the next the next endpoints function, so the 4-point function or the tri-spectrum. But of course, yeah. So, and then you can continue that hierarchy of endpoints functions.
Then have you ever tried to do this at higher redshift, meaning that at some point nonlinearity will, you know, the additional information will not escape to higher order endpoint statistics. So
right.
P cross P and field level inference at high redshift should be the same.
Yeah, that's a good question. So, but of course, it's not as simple as, you know, just going to high redshift. It also depends on the tracers, right? And how the tracers are biased of the underlying large-scale structure fields. But yeah, exactly, that's what we did here. So we looked into the snapshot from simulations at 2 different redshifts from 0.5 to 1, and you kind of see that the improvement factors kind of decrease. So it's not as impressive in this case where you go to redshift of 1, right? So yeah, I think in general that would be one thing that I would say that kind of expected as you go to higher redshift. The scale that the linear scales become, you know, more and higher Ks, right? So you need to push even further to get more. But yeah.
So I have a kind of follow-up questions.
Mm-hmm.
I'm trying to understand the current limitation of the field level inference plus EFT. So
Right.
could you go to the slide where you show the beyond 2-point challenge?
Yes.
And is this a blind analysis? And also, my naive guess is because you don't recover the unbiased result
Right.
with this K cut. Is that because if you go to more aggressive K cut, you actually further away from the
Yeah, that's a very good question. I didn't have time to explain in the talk. Maybe I should have. Is that here there are two error bars. So the solid one is the one before unblinding, and this one is the one that we corrected for after unblinding. And the difference is basically, so this one, it corresponds to the result that I show, the modeling and analysis choices that I show you in other results. This one is a bit more aggressive. So this one, for example, use a simpler model, a simpler forwards model, a simpler model for galaxy bias, and a simpler model for the stochasticity. So this explains why the error bar here is much smaller than the error bars here. So I think what this exercise or challenge told us is that in order to do field level inference robustly, we need to go to certain orders of the forwards model, and we need to account for certain stochasticity.
So you mean this bias is the issue is solved once you use a more complete calculation. So
Right.
it's a trade-off between
Right.
It's not an issue in the methodology,
Sorry.
it's a computing efficiency.
No, it's a modeling choice issue. So for example, here, the solid error bars are basically correspond to doing this expansion only up to second order.
Yeah.
And only treating this quantity here as a fixed Poisson, so treating the galaxy stochasticity at the Poisson short noise. As soon as you go to third order and you allow for the galaxy stochasticities to be something beyond Poisson, also has some kind of scale-dependent correction, then everything becomes unbiased again. And this is what we did in the other results.
So you mean there will be more nuisance parameters, but they will be marginalized over here?
Right, so depending on, I think what I'm trying to say is depending on the type of galaxies, the type of tracers that you're looking into, you might need to go, and the scales that you are analyzing the data, you might need to go to higher order, or you need to have a more complicated or sophisticated model for the galaxy stochasticity.
And what's the smallest scale that EFT can go?
You mean the smallest scales that we can push? Again, this is also like Tomomi hinted on, this depends on the redshift. But let's say redshift 0, you expect EFT to fail somewhere before like K of 0.25. So that is the nonlinear scales. But you expect EFT to fail even before that.
Mm-hmm.
So, yeah.
Yes, yes.
Yeah, please.
So, I think that the issue about using summary statistics,
Right.
to use the higher order statistics, is we don't have an accurate way to estimate covariance.
That's right.
Because we measure tri-spectrum, we cannot estimate the error properly. So, what's the situation for the field level? Can you estimate the covariance or error properly?
Right. Yeah, so here we actually do not estimate the covariance, but we have a model for the covariance. So this is our covariance actually. So the model for the galaxy stochasticity is basically the covariance. So, and depending on the types of tracers, you might need a more sophisticated model for the stochasticity or for the covariance. But in the covariance, there will be free coefficients that then you need to fit to the data. But in this approach, you do not estimate the covariance and then fix it like you would do in the summary statistics.
If we believe what you said, so the actual information kind of tri-spectrum higher order statistics, that means that you are utilizing the completely non-Gaussian information,
Right.
But not such a very simple way to estimate. I mean, I'm afraid that you are over-constraining.
I see your concern. Yes, so this is, I agree that this somewhat simplifies model for stochasticity. Actually, this is what DESI is now using for the power spectrum. But I agree that I think your concern is like if you use higher order statistics, information from higher order statistics, do you need a more sophisticated model? Well, the answer is a bit unclear yet. I think in practice, we are now trying the covariance. We can actually, I think the good thing about EFT is you know for sure which kind of contribution should appear, or the form of the contribution at least, and then you try until the points where you see unbiased constraint. So, for example, I can continue this expansion and I can go to something with a k to the fourth correction, or I can add density dependent noise. Sorry if this is getting a bit technical, but this is the point is that you know the form of the covariance, you know the form of the stochasticity, and then you try to fit these free coefficients to the data. But of course, I agree that there's no, before looking at the data, there's probably not a lot of hints of which kind of contribution you might need.
So assuming that, for example, we have an infinite computational resource, and
Yeah.
if you can make super many mocks, then is there a way to get the correct covariance like from the whole mock?
When fitting to the mock, you mean? Yes, I think you can, but then you run into the issue of whether you trust that the mock is represent a faithful representation of the data that you're going to observe. So that's the same issue that power spectrum or pi spectrum or any summary statistic analysis are facing, right? So yeah, but we plan to study this problem in a more systematic approach in the future, so that we can generate mock with different contributions, different types of forms of contribution of stochasticity, and then we can try to fit the data using with misspecified assumption, for example, and then we see how this affects the results. Yeah.
So probably just a naive question. So
Yeah.
does the computing time linearly scales with the volume of data?
Right.
Or it's exponential?
Yeah, this is a very good question. So the volume, the thing is like I said, right? So for a given volume, we want to cover the entire volume with voxels. So basically the number of parameters scale at roughly at the same as the right. So the number of parameters scale the square. The cube, right?
Yeah.
Right. So so the computational power is not time is not a problem. The more problem is that as you have more parameters, then your sampling process is a bit slower.
Exactly.
Yeah. So, but the scaling of this sampler that use gradient information is basically go as d to the power fifth to the fourth. So it's not as bad as a simple random walk, Monte Carlo random walk, but of course it still increase roughly more than linear. Yeah. Right.
How bad it could be?
You mean like for some like okay? So let's say for
in terms of number of how the scales with number of parameters.
right. So typically for the current volume of galaxy surveys, I would expect you need like about a week for this kind of analysis, for a run of this analysis. The good news is you can parallelize it. You don't have to, you just run one single chain. You can run multiple chains, right? So even though each single chain can take a week, by the end you can still speed it up and then combine them together for the analysis. So I wouldn't say this is impossible. But of course, we are working very hard on improving the computational time, and also even more important, the sampling efficiency, because that's the critical answer why the computational time is really not a bottleneck.
Okay, any more questions? Yeah, Timothy?
So when does field level inference become ready to explore full cosmological parameter space? What is the bottleneck right now?
Yeah, so I don't think having other cosmological parameters beyond sigma 8 is an issue. It's just a simple. It's a simple solution that you just need to implement the power spectrum, or you just need the gradients of how the input power spectrum change with respect to the cosmological parameters. So this is also a work in progress. The only reason that we haven't done it yet is but actually many people have already done it. But for me, I haven't done it yet just because I have been focusing on getting the constraint on sigma 8 to be unbiased. But having other cosmological parameters I don't think it will change the issue. I will introduce additional deterioracies, at least for this problem that we're looking for galaxy clustering. For other props, maybe, but for galaxy clustering, getting sigma 8 is really just about breaking the deterioracy between B delta and sigma 8. So it's, yeah.
Okay, we're at the hour, so let's close, but we can continue the discussion after.
Sure.
And there should be tea and coffee served outside. Let's thank Minh again.
Thank you.